Have you ever looked up into the deep dark velvet of the night sky and wondered? The stars glitter like scattered diamonds, beautiful and distant. But have you ever asked yourself a truly profound question? Why is it dark at all? It seems like a simple, almost childish question. The sun goes down, so it gets dark. But for centuries, this simple observation posed one of the greatest puzzles in all of science. The darkness itself was a contradiction, a mystery that hinted at a much deeper truth about the nature of our reality. It suggested that our common sense assumptions about the universe were fundamentally flawed, and the answer would change everything we thought we knew. This puzzle has a name: Olbers Paradox. It was made famous by the German astronomer Heinrich Wilhelm Olbers in the 19th century, though others had pondered it before him. The logic is deceptively simple. Imagine for a moment that the universe is infinite. Imagine it is filled with an infinite number of stars, scattered more or less evenly throughout endless space. If this were true, then no matter where you looked in the night sky, your line of sight should eventually end on the surface of a star. There would be no empty, dark patches. Every single point in the sky would be as bright as the surface of our own sun. Think of it like standing in the middle of a truly gigantic, endless forest. No matter which direction you looked, your view would be blocked by a tree trunk. You wouldn't see any open sky beyond the forest because the trees would fill your entire field of vision. If the universe were infinite and full of stars, the same principle should apply. The night sky should be a solid, blazing wall of light. It should be overwhelmingly bright day and night without a moment of darkness. But it isn't. We look up and see a profound, beautiful, and mystifying darkness between the stars. This simple observable fact that the night sky is dark tells us something fundamental must be wrong with our starting assumptions. Either the universe is not infinitely old, or it is not infinite in size and static, or both. The darkness is a clue, a cosmic breadcrumb left for us to follow. It beckons us to explore the true nature of the cosmos, to understand its origins, its scale, and its ultimate destiny. The solution to this paradox is not found by simply looking up, but by understanding the grand story of the universe itself, a story that begins with a single explosive moment. The story of our universe, as we understand it today, begins not in a state of infinite calm, but in an unimaginable cataclysm. About 13.8 billion years ago, everything we see, everything we are, was compressed into a point of nearly infinite density and temperature. This was not an explosion in space, but an explosion of space itself. This moment is what we call the Big Bang. It was the beginning of time, the beginning of space, and the beginning of the great cosmic expansion that continues to this very day. In that first searing moment, the universe was a roiling soup of pure energy, matter, and antimatter, expanding and cooling at an incredible rate. From that singular point of origin, the universe began its long and epic journey. As space stretched, it cooled. Energy condensed into the fundamental particles that would eventually form atoms. Over hundreds of thousands of years, these particles combined to create hydrogen and helium, the raw materials from which the first stars and galaxies would be born. The universe was not a static stage on which cosmic events played out. It was an active, dynamic entity, constantly growing larger. This concept of an expanding universe is one of the most important discoveries in the history of science, and it holds the key to understanding the darkness of the night sky. This expansion is not like an explosion pushing matter out into an empty void. Instead, the very fabric of space-time itself is stretching. A good way to visualize this is to imagine baking a loaf of raisin bread. As the dough rises and expands, the raisins move away from each other. A raisin located anywhere in the loaf would see all the other raisins moving away from it. From our vantage point in the Milky Way galaxy, we see the same thing. Distant galaxies are not flying through space away from us. Rather, the space between us and them is expanding, carrying them along for the ride. This cosmic expansion has a crucial consequence. The farther away a galaxy is, the faster it appears to be moving away from us. This isn't because it has a bigger engine. It's because there is more space between us and that galaxy to expand. This relationship, discovered by Edwin Hubble, revolutionized our understanding of the cosmos. It confirmed that the universe was not the eternal, unchanging place that many had assumed. It had a beginning, it has a history, And this history of relentless expansion is written across the sky, visible to anyone with the right tools to see it. Because the universe had a beginning and light travels at a finite speed, there is a fundamental limit to what we can see. Light from the most distant objects in the cosmos has been traveling for billions of years to reach our telescopes. Since the universe is 13.8 billion years old, you might think that the farthest we could possibly see is 13.8 billion light years in any direction. But the story is more complex and far more vast because of the continuous expansion of space. The light from a distant galaxy may have started its journey when that galaxy was much closer to us, but during its multi-billion-year voyage, the space it was traveling through has stretched tremendously. This brings us to the concept of the observable universe. This is the portion of the total universe from which light has had enough time to reach us since the Big Bang. It is a sphere with us at the very center, not because we are special, but simply because we are the ones doing the observing. An observer in another galaxy would have their own observable universe with its own unique boundary. The actual diameter of our observable universe is not 27.6 billion light-years, but a staggering 93 billion light-years across. This is because the objects at its edge have been carried much farther away by cosmic expansion since they first emitted the light we see today. Within this vast sphere of vision, there is another important conceptual boundary known as the Hubble Sphere. This is a region around us, about 14.4 billion light-years in radius, beyond which galaxies are receding from us faster than the speed of light. This might sound like it violates Einstein's theory of relativity, which states that nothing can travel through space faster than light. However, this is not about motion through space, but the expansion of space itself. The fabric of space-time is not bound by the cosmic speed limit. Galaxies beyond the Hubble Sphere are being carried away so quickly that any light they emit today will never be able to overcome the expanding space between us and them. It will never reach us. So we are surrounded by cosmic horizons. The observable universe is the absolute limit of what we can ever know about, the boundary defined by the age of the universe. Within it, the Hubble Sphere marks a point of no return, a boundary beyond which communication and travel are forever impossible. We can still see the ancient light from galaxies that are now beyond this sphere, light that was emitted long ago when they were closer. But we are watching ghosts. The galaxies as they exist today are already beyond our reach, their light fighting a losing battle against the ever-stretching cosmos. Now we can finally return to the riddle that started our journey. Why is the night sky dark? Olbers Paradox was built on two faulty assumptions: that the universe was infinitely old and static. The Big Bang and cosmic expansion shatter both of these ideas. First, the universe is not infinitely old. It has a finite age of 13.8 billion years. This means we can only see the light from stars and galaxies that are within our cosmic horizon. Light from anything farther away simply has not had enough time to reach us. The forest of stars does not go on forever. It has a starting point in time and therefore a limit in space that we can perceive. The second and perhaps more powerful solution is the expansion of space itself. As distant galaxies are carried away from us by the stretching of space-time, the light they emit is also stretched. This phenomenon is called cosmological redshift. Think of a light wave like a slinky. As the space it travels through expands, the slinky is pulled apart and its waves become longer. For visible light, this stretching shifts the color toward the red end of the spectrum. The farther a galaxy is, the faster it recedes, and the more its light is redshifted. This stretching of light is the ultimate answer to Olbers Paradox. For the most distant galaxies we can see, the ones near the edge of our observable universe, their light has been stretched so profoundly that it is no longer visible to our eyes. It has been shifted completely out of the visible spectrum, into the infrared, microwave, and even radio wave portions of the electromagnetic spectrum. So, when we look into those seemingly empty patches of night sky, we are not looking at nothing. We are looking at light that has become invisible to us, its energy diluted by a 13.8 billion year journey through an expanding universe. The sky is dark not because it is empty, but because our eyes are not equipped to see this ancient stretched out light. When the Hubble Space Telescope pointed its sensitive instruments at a tiny, seemingly blank patch of sky for hundreds of hours, it captured an image called the Hubble Deep Field. It revealed over 3,000 galaxies in a speck of sky no bigger than a grain of sand held at arm's length. The paradox was solved. The night is dark because the universe is young, expanding, and the most distant light has been redshifted into invisibility, a faint, ghostly echo of a once brighter cosmos. So, we've established that our view of the universe is finite, but this doesn't really answer the ultimate question: is the universe, beyond what we can see, finite or infinite? To tackle this, cosmologists turn to the geometry of space itself, as described by Einstein's theory of general relativity. The theory tells us that mass and energy curve the fabric of space-time. A little bit of mass, like a planet, creates a small curve that we experience as gravity. But what about the overall curvature of the entire universe, determined by all the matter and energy within it? On the grandest of scales, there are, three main possibilities for its shape. One possibility is that the universe has a positive curvature, kind of like the surface of a giant four-dimensional sphere. In such a universe, there wouldn't be any edge. If you could travel in a straight line for long enough, you'd eventually loop around and end up right back where you started, much like sailing around the Earth. This kind of universe is finite but unbounded. Parallel lines of light traveling through it would eventually converge, and the angles of a giant triangle drawn between three galaxies would add up to more than 180 degrees. This would happen if the total density of matter and energy in the universe was above a certain critical value. A second possibility is a universe with negative curvature, shaped sort of like a four-dimensional saddle or, a Pringle chip. This shape is open and infinite. In this scenario, parallel lines of light would diverge, moving farther and farther apart as they traveled. The angles of a cosmic triangle would add up to less than 180 degrees. This kind of universe would stretch on forever in every direction, never looping back on itself. This geometry corresponds to a universe where the total density of matter and energy is below the critical value. It's a universe without end, a boundless curving expanse. The third possibility is a universe with zero curvature. We call this a flat universe. This doesn't mean it's two-dimensional like a piece of paper, but that the rules of Euclidean geometry we learn in school apply on the largest scales. Parallel lines of light would remain parallel forever, never meeting and never diverging. The angles of a triangle would add up to exactly 180 degrees. A flat universe, like a negatively curved one, would also be infinite in extent. It would go on forever without boundaries. This specific geometry occurs if the universe's total density is precisely equal to the critical density. Determining which of these three shapes describes our universe seems like an impossible task. How can we measure the geometry of something so vast, especially when we are trapped inside it? The key lies in finding the biggest possible triangle we can measure. Fortunately, the universe has provided one for us. The evidence is imprinted on the oldest light in the cosmos, the cosmic microwave background, or CMB. This is the faint residual afterglow of the Big Bang, a wall of light emitted when the universe was just 380,000 years old, and it fills all of space. The CMB is not perfectly uniform. It's actually mottled with tiny temperature fluctuations, small hot and cold spots that represent the seeds of all future structures, including the galaxies we see today. Scientists have been able to measure the typical size of these spots with incredible precision using probes like WMAP and the Planck satellite. They know how large these spots were in the early universe, and they can see how large they appear to us today across 13.8 billion light-years of space. This cosmic scale observation forms the largest possible triangle we can draw. Two sides are the lines of sight from Earth to opposite edges of a spot, and the third side is the spot itself. By measuring the apparent size of these spots in the sky, we can determine the geometry of the space the light has traveled through. If the universe were positively curved like a sphere, the spots would appear larger than expected, as if viewed through a magnifying glass. If the universe were negatively curved like a saddle, the spots would appear smaller than expected. But the data from our most precise measurements have shown something remarkable. The spots appear exactly the size they should be if the light has traveled through a space with no large-scale curvature, the evidence overwhelmingly points to the third option. On the largest scales, our universe is flat. The angles of this cosmic triangle add up to 180 degrees. This measurement is one of the pillars of modern cosmology. It tells us that the density of matter and energy in the universe is astonishingly close to the critical value required for flatness. This finding has profound implications. While it doesn't definitively prove the universe is infinite, it strongly suggests it. A flat universe, by its geometric nature, extends infinitely in all directions. The observation that the universe is flat leads most cosmologists to a stunning conclusion. The universe is very likely infinite. If space has no overall curvature, then the simplest and most logical model is one that continues forever. While it is technically possible that our universe is just a very, very large sphere, so large that our observable patch appears flat, just as a small patch of the Earth's surface seems flat to us, the principle of Occam's razor suggests we should favor the simpler explanation. An infinite flat universe is the most straightforward interpretation of the data we have collected. This idea fits perfectly with our leading theory of the universe's first moments, known as cosmic inflation. Inflation theory proposes that in the first fraction of a second after the Big Bang, the universe underwent a period of hyper-accelerated expansion, growing from a subatomic size to something astronomically large almost instantaneously. This process would have stretched any initial curvature of the universe to such an enormous scale that, for all practical purposes, it would appear perfectly flat within our observable horizon. Inflation naturally produces a flat-seeming universe, which is exactly what we observe. Of course, science is never about absolute certainty. It is possible that our observable universe is just one tiny flat-looking region on a much larger curved hypersphere. Some calculations suggest that if the universe is a sphere, it must be at least 1,000 times larger than the part we can see. In this scenario, the universe would be finite, but so incomprehensibly vast that we would never be able to detect its curvature or travel far enough to loop back around. For all intents and purposes, it would behave as if it were infinite from our perspective. So, while we cannot send a probe beyond our cosmic horizon to check, the combination of observational evidence and theoretical models has built a strong case. The flatness measured in the cosmic microwave background, supported by the theory of cosmic inflation, has led to a powerful scientific consensus. Most cosmologists today operate under the working assumption that the universe we inhabit is not only expanding, but is also spatially infinite, a boundless expanse of space, time, matter, and energy extending forever. If the universe truly is infinite, the implications are, well, mind-bending. An infinite space filled with a finite number of types of particles can only arrange those particles in a finite number of ways. Given an infinite amount of cosmic real estate, the laws of probability dictate that any possible arrangement of particles must repeat, not just once, but infinitely many times. This leads to a startling and profound conclusion. There are other worlds out there that are identical to Earth, with people on them who are identical to you. This isn't science fiction, but a logical extension of the concepts of infinity and quantum mechanics. The number of possible configurations of particles within a given volume of space, say the size of our solar system, is astronomical, but it is not infinite. If you travel far enough through an infinite cosmos, you are statistically guaranteed to eventually encounter another region of space where the particles have arranged themselves in precisely the same way as they have here. There would be another Earth orbiting another sun, with another version of you living a life identical to your own. The distances involved are beyond human comprehension. One estimate suggests that an exact copy of our observable universe, a sphere 93 billion light-years across with every particle in the same position, exists at a distance of 10 to the power of 10 to the power of 118 meters away. That number is so large that writing it out would require more zeros than there are particles in our own universe. And that's just for an exact copy. Worlds with minor variations, an Earth where you chose a different breakfast this morning, or where the dinosaurs never went extinct, would be much closer. though still unimaginably far away. These other worlds, these other versions of ourselves are fundamentally unreachable. They lie far beyond our observable universe, forever hidden from our view by the cosmic horizon. Due to the accelerating expansion of the cosmos, we are locked into our own local patch of space-time. In fact, 94% of the galaxies that we can see in our night sky, even within our observable sphere, are already receding from us faster than light. They are already unreachable. We see their past light, but we can never visit them, forever separated by an ever-widening gulf of expanding space. The relentless expansion of the universe not only separates us from potential parallel worlds, but is also actively erasing our view of the cosmos. Every second, the expansion of space carries about 60,000 stars permanently beyond our Hubble Sphere, the point at which their light can no longer reach us. They cross a cosmic event horizon and vanish from our future. We are living in a privileged moment in cosmic history, a time when the sky is filled with countless galaxies, each a testament to the Big Bang and the vastness of the universe. But this spectacular view is temporary. As time goes on, the accelerating expansion will carry more and more galaxies beyond our reach. In about 100 billion years, every galaxy outside of our own local group, the small cluster of galaxies that includes Andromeda and is gravitationally bound to us, will have receded beyond our cosmic horizon. The night sky for future astronomers will be a far emptier, lonelier place. They will see the stars of our own merged galaxy, the so-called Milkomeda galaxy, but beyond that, only an endless starless void. Looking further into the future, around 2 trillion years from now, the expansion will have stretched the light from even the closest receding galaxies so much that they will be completely redshifted out of visibility. All evidence of other galaxies and of the Big Bang itself will have been erased from the sky. A civilization of intelligent beings arising in that distant future would look out into the cosmos and see only their own island galaxy. They might logically and incorrectly conclude that their galaxy was the entire universe, eternal and unchanging. They would have no clue about the true dynamic history of cosmic expansion. We therefore stand at a precious cosmic dawn. We are fortunate enough to live in an era where the evidence of our universe's origin and evolution is still written across the sky. We can see the distant galaxies and measure their retreat. We can detect the faint afterglow of creation itself. The darkness of the night sky, once a paradox, has become a guide, leading us to understand our place in an expanding and likely infinite cosmos. The universe is a story that is still unfolding, and while its ultimate fate may be one of growing isolation, its present reality inspires nothing but wonder.